Don Wilkinson.
Thanks, Larry, and thanks, Healthy River Partnerships, for having me speak tonight. So the title of my talk is Farmville 3.0, Evaluating the Success of Integrated Farming Practices in Northern Missouri. And I must say that this work has been supported by the Missouri Department of Natural Resources, and it's part of the USGS Cooperative Water Science Program. So why Farmville 3.0? So I want to talk about scale. That's part of it. Let's local scale, as Larry said. The area that we're looking at are tributaries to the Missouri River, and then scale that up to the Missouri River and then to the Gulf of Mexico to make some connections between those. And another reason that I wanted to call it Farmville 3.0 is that conservation programs in the United States aren't really new, but issues around them remain. And there's been sort of historically three main agricultural conservation programs in the United States. And they've often come about in response to environmental disasters such as the Dust Bowl in 1935, or kind of renewed understanding about conservation issues such as the Gulf hypoxic zone, which I'll talk more in detail about, which we've come to understand a lot about. And these programs are incentive-based, but we really don't have a lot of information about how well they work. So the first program was really called a set-aside program. So we paid farmers to not either grow things like wheat or corn, and farmers, being astute business people, just decided to grow a different crop, which is not necessarily a very effective conservation measure. In 1986, the Conservation Reserve Program, which is probably considered by many to be the most effective environmental agricultural conservation program, basically pays farmers a small amount of money to not grow crops at all on the most erodible land. And that, it began in '86 and it ramped up, but in more recent years, as government funding has begun to shrink, we've moved to a different kind of program, which really began in the early Bush II years, and that's called Working Lands Conservation. And that's where the assumption is that farmers can still grow crops on the land, but we can do certain kinds of conservation measures that actually can improve water quality. But again, we really don't know. So what we've typically done is we determine the success of the program based on how much money we spend on it. And as resources get fewer and fewer, there's discussion about whether or not are we effectively spending our money. So in 2010, the U.S. Department of Agriculture increased support for these integrated conservation measures. And those run the gamut from many different things, riparian buffer zones, terraces, so farmers can get some funds to help them do these sorts of things. Tile drains, rotational grazing, there are all kinds of things. No-till legume cover crops, tillage radishes. So this money was earmarked for certain watersheds, such as the Grand River and other basins in the Missouri and Mississippi River that were known to provide a lot of nutrients ultimately to the Gulf of Mexico. So integrated farming practices on the land, like if you were to drive past them, it may be a little difficult to see, but here's some terraces here. There's some tile drains that from an aerial photo, you can't really discern what these might be. And there's not a Farmville, but there's actually a Farmersville in the study area. Things like waste lagoons that help alleviate issues with manure management, all of these things fall under the province of integrated farming practices. And the reason that the USDA applied a lot of money to this program is that goals in terms of reducing the size of the Gulf hypoxia zone were not being met. So here's the goal of the task force down here, this black line, which is 5,000 square kilometers. And so some of this can naturally occur, and I'll talk about how that happens. But we're not, under very few circumstances, we're meeting this goal. In fact, the 5-year average is almost 3 times that goal. So we need to do something about that, and I'll explain why we need to do that. And so here's a little cartoon of hypoxia. It's also similar to eutrophication. So really what happens is nutrients, either in the form of runoff from agricultural fields or from wastewater treatment plants or urban lands, are delivered into some kind of river or water body, and then energy in the form of sunlight allows algae to grow in these water bodies. And what can happen is if there's enough energy and excessive nutrients, then this algal growth can get pretty far. And eventually it blocks the sunlight at depth, and the algae that's grown here, these algal matter, begins to die and sink to the bottom. And when it does, bacteria begins to decompose it, and it consumes all the oxygen, which the fish and other organisms need to survive. So if you can't move away from this zone, then you're going to die. And so some things can move away from that zone, but some of the lower critters in the food chain, which support the other food chain, perish. And the hypoxic zone is sort of a seasonal phenomenon. So this is an image from 2008. So in the summertime, so all this red here is dissolved oxygen levels that are below 2 milligrams per liter. So we have a large area, and 2 milligrams per liter will not sustain aquatic life. So we have a large area of really depleted oxygen. It's sometimes referred to as the dead zone. And in the summertime, and this is also the time when most nutrients are transported either through runoff into the Gulf of Mexico, and it's also a time when a lot of energy through sunlight is being transmitted into the system. So in the fall, when the temperatures cool down and there's less mobility of nutrients, the system can kind of revert and sort of rectify itself. But this happens basically every year. And it's not just a phenomenon that's only to the Gulf of Mexico. In fact, it's occurring throughout the coastal areas of the United States, in Europe, actually all throughout the world. And so it's a problem not just for us, but for other areas as well. And what does it look like? So this is what I call the faces of hypoxia. So this is a red tide in California. This is a large fish kill from an area where the fish couldn't move away from this dead zone. There's some incredible algal mats. Here, this is a drinking water reservoir, and they've erected a barrier to try to keep this algae from going into the drinking water reservoir because the algae can affect taste and odor issues of water during the water treatment process. And then here's a picture that was taken in Farmville, as I call it, in late summer, and you can see there's floating algal mats all along the top. This is closer to home. This is in Kansas City. This is the lower end of Brush Creek. And this is showing that almost the entire stream is choked with either macrophytic algae that grows along the shore or floating algae. And that's because there hadn't been there hadn't been enough precipitation to sort of flush through the system. And in Indianapolis, they had these special kind of farming devices that actually have to go in. The streams are so full of nutrients, they have to basically every day to farm these floating algal mats to keep this stream, which provides drinking water to the city of Indianapolis, from being completely choked and stopping the flow of water. So there are costs associated with that. Not just, there are true monetary costs, but there's also environmental costs. And here's another way that we scientists like to look at things, are these crazy kind of graphs, but this was taken just over the last 45 days at a stream here in Kansas City, Indian Creek near State Line. And so what we're showing here, this is a system, and that shows, so they're measuring nutrients in this system, this is the green line, every 15 minutes. So this is a system, because of wastewater effluent, that gets ample nutrients. There's plenty of nutrients in this stream. And here we're measuring energy basically through water temperature. And so in the wintertime, the temperatures kind of keep things down, but as soon as spring arrives and the temperature goes up, or energy is input into the system, what you can see is a response in the dissolved oxygen. So some of these ups and downs here are just related to the solubility of oxygen as temperature changes. What you can see is as energy goes into the system, then the dissolved oxygen pretty quickly declines to this threshold. This is not a chronic threshold, but a more of an acute threshold for aquatic life. And it's touching on this 5 milligram per liter line. And then we have a small runoff event that actually brings some oxygen back into the system and sort of rectifies it, and then it cooled off. And if I were to extend this graph into today and into the week, it would probably begin again to come down here again. And one of the things that happens is because this time of the year there's usually ample nutrients, there's ample energy, but there aren't predators that are actually grazing on the periphyton, so this can be some of the most productive times for streams in terms of nutrients. So, as Larry said, tributaries matter. So we looked at the Grand River Basin in northern Missouri, and again, because resources are limited now, we had to rely on an existing network of other stream gauges and long-term record to help us make sense of what was happening in this basin. So we put some gauges here, but we had to rely on these other things, and thankfully we had them in order to look at what was happening. So the objectives, and I'm only going to talk about two for the study, were to characterize concentrations and loads of nutrients for streams within the lower Grand River Basin, and how much of those nutrients are exported from the basin ultimately to the Missouri River and then onto the Gulf of Mexico. Because what we know is once it goes into the Missouri River, the processes that would sort of remove the nutrients generally aren't there. Some of it can happen, but in general, most of the time, it just keeps going. And to evaluate the water quality in this historical context. So I'm going to give you the lessons right now, and then after that, if you want to refresh your beers, you can do that. So we have a good understanding of nutrient dynamics in the basin. We understand seasonal and annual patterns. We have a better understanding of potential sources. And we understand implementation of the integrated practices within the context of long-term patterns and how those patterns might vary with time. So how did we do it? So we did monthly sampling plus spring runoff. I'm going to talk about the first 44 months of the study. And we sampled for flow nutrients, and I'm not going to talk about these other things that we also sampled for. And so the progress to date is really, we have daily, monthly, and annual estimates of nutrients, and by that I mean nitrogen and phosphorus in the system. And we have instantaneous and daily stream flow. And I'm going to talk about a couple of, not going to go into great detail, but a couple of models that really help us understand, give us better understanding of the system. And so all the models, we're collecting data in the field, and those go into feeding these models. And what that allows us to do is, it's just too expensive to sample every day. It allows us to extend our understanding of the system. And this research should be being published soon in River Research and Applications. So it's important to know that the study area and much of the United States were in drought during the first part of the study. So this is the U.S. Drought Monitor, and the yellow, the red is the driest part. So we're looking at this area up here. So this is October of each year. So it was definitely a dry period, at least for parts of the year. So that's one way to look at that. And then here's a more sort of geeky way to look at it. This is the long-term precipitation. This is cumulative precipitation for the first part of the study. So this blue line is how much precipitation we would expect based on a number of precipitation stations in the area. And then this is the precip at all the stations in the basin. So these are all below that pattern. So another important thing to note is that certain times of the year, primarily February through June of each year, the precipitation was either near normal, or in some cases in 2013 we had a very wet spring, much above normal. So you can be in a drought and still have these wet periods. And now I'm going to talk about this model, this weighted regressions against time, discharge, and season. So this graph is just a bunch of, this is output that shows that we can calibrate the model using the data that we have. So this model requires 20 years of data and 200 data points, which is something we don't always have. But by doing that, it allows us to, which is importantly, remove year-to-year hydrologic variations, but still look at the seasonal variations. And we can compute concentrations and flux, or the amount that comes out of the system, for every day in the record. And we can adjust for flow, which is really important if we're trying to look at system changes. Because we know that hydrology, the amount of runoff, makes a huge difference. And here's some other output. This is for the Grand River. This is total phosphorus. So we can look at this. It's easy to see that if we look at, this is discharge increasing in this direction, and this is concentration. So it's easy to see that there's definitely a relationship between concentration and discharge. That's very easy to see. And this is showing that there's a seasonal component, like it's increasing in the spring and summer. These plots show that the days that we sampled are very consistent with the days of the record, which is important for modeling. But here, this shows the concentration by year, and it's a little more difficult to determine if there's really a pattern there. So that's what we're really trying to do is eke out a trend. Are concentrations increasing or decreasing over this time frame? And we know that streams are fundamentally dynamic systems, which is, I think, why we love them so much, but it makes them difficult to study. And this tool really helps us with a great understanding of what's going on. So if we look at, this is the Grand River again, this is phosphorus. So this line is what's called a flow normalized. So now we're taking out the effects of flow. So we have two things here. The red dots are non-flow adjusted, and this is the flow adjusted. This is concentration up here, and this is flux, or the amount that's exported. So both of these are showing an increase over this time frame of 1991 to 2013. But if we could find out what's really happening, it would be very useful. So what is really happening? So what we can do is we can then begin to separate these out by season. So this is February through July of each year. So now we're looking at just samples that were collected for discharges below 1,240 CFS. There doesn't appear to be much, there's not really a pattern there that you can see. But if we look at samples collected at flows greater than 1,240 CFS, now a pattern looks like it begins to emerge. And we can use these plots, this is called a contour plot, to really help us understand what's going on. So this is for any given year over this 1990 to 2013 time frame. So for each month, this is showing what's happening during the year. And this is the low range of flow on this end here. And this is the high range of flow. So what this is showing is that for most of the year, under most flows, there really isn't much going on there. There's some increases in some and decreases in another, but the real thing that's happening is under high flows in the spring and early summer, there's been a big change in concentrations over this time frame. And there does appear to be a flattening in later years. And we can look at the same thing for total N. This is over that same time frame, and we see a very similar thing. It's the concentration changes are really reflected over this high flows. In this case, it's a little earlier than the phosphorus, late winter to summer. But we can also break it apart by decade and really find out that most of the changes that we see here really happened in the first 10 years. And since 2002, there's almost no change in concentrations. We've also determined that there's a late winter snow melt and storms. We didn't have those this year. Those can really transport a lot of nutrients into the system. And why would that be the case? And this plot here is showing this is the total nitrogen concentration in the Grand River. Okay, the average total nitrogen concentration. So it peaks in basically April, and this is the excess soil moisture in the ground during the same time frame. And that's showing that. So when we're planting our crops, we need nutrients, and we're also cultivating the land. So that's when there's excess soil excess soil moisture. That's a good time to plant crops. So as soon as those grow, those begin to take moisture out of the ground and pretty much lock up the system, so transport is greatly reduced through the rest of the year. And then as we begin to harvest those in the fall, then soil moisture begins to return to the system, and this thing repeats itself. So it leads to what I call the sort of ball cap system of transport. So if you look at this from the side, if you imagine this is a baseball cap, so that's why I call it like that. It's sort of this what it looks like. We know that most of the transport, more than 70% of the transport, and these are the large streams in northern Missouri, the Grand, the Platte, the Missouri River, the Sheraton, those are up here. The Missouri River is down here. Most of the transport is occurring over this February through August time frame. And then because there's less precipitation, there's less available nutrients, things don't really change much in any given year. The curves for the Missouri River are flatter because the hydrology of the river is a lot different. It's regulated to some extent by releases. It's a much larger basin, so there's things that can kind of dampen this curve. But if we want to really understand are things changing in the watershed, we have to adjust for flow. We have to take this sort of seasonal variation out of the picture. And so that's what these are showing. So the upper one is total nitrogen concentration. These are adjusted for flow. And total nitrogen flux, so the amount taken out of the basin. So the other thing I want to point out is these are generally flat curves. I mean, there's some increase and decrease, but for the most part, for the main rivers, the larger rivers in northern Missouri, these curves are generally flat for total nitrogen. There's a big difference in total phosphorus. Those curves are on the increase. So why would that be the case? I mean, that's very different between those two nutrients. And if we look at it like this is the total change in total nitrogen concentration average for those same streams. So it's decreased by 5%. And total phosphorus has increased by almost 40%. So a huge difference between those two. So why is that the case? And we think one of the reasons it's the case is because the system, so this is a nutrient budget for nitrogen for the 10-county study area that we looked at. And the gray area indicates there's basically a deficit of nutrient in terms of the crop needs for the system. And so since the mid-'70s, there's been mostly a deficit of nitrogen in the system. And for phosphorus, the phosphorus budget looks entirely different. There's still an increase. It looks like we've maybe changed things and got a better handle on phosphorus. But in many cases, there's too much phosphorus in the system. So where's it coming from? The biggest increase in phosphorus and the major row crop in the study area are soybeans. Has been an increase in soybean P application rates. So since 1990, there's the increase in soybean application rates. And another source of phosphorus in the system, this graph is showing the relationship between the amount of fertilizer P on this curve and the amount of manure P in the system. And more recently, manure P has begun to exceed fertilizer P. And so it's really not uncommon for in the late winter to see these sorts of essentially minefields of fertilizer that are on the landscape before the grass begins to grow up and lock into these nutrients that are basically ready to be mobilized by any kind of precipitation event. So now we get to the questions, are integrated conservation practices improving water quality? So we have the study area. Now we only have 44 months. We don't have the luxury of looking at more than 20 years of data. So we have to use a different model to do that. These graphs are just showing that we can calibrate a model that allows us to understand how many nutrients are being exported from the basin. But it is a shorter time frame, so we have to use different tools, and we did look at making sure that those two models, the output of those were comparable. So these graphs, I mean, there's a lot of data here, but the important thing is we know we have a good handle on how many nutrients were exported from these tributaries over this time frame. That we can do. And we also know that this period of February through June of each year, like in the study area time frame, more than 95% of the nutrients were transported from these tributaries into the Grand River. So we have a good handle on that. So if you're looking to make changes in the system, this might be a good place to focus your resources. Because if you focus resources in the other time frame, you're going to have you're only looking at 5% of the total nutrients. So, but now, how do we compare that? Since we don't have this long-term record on these tributaries, what we can do is we can look at the Grand River, the receiving stream, and we measure that for these same 44 months of implementation. So this is what we observed during those 44 months for total nitrogen, and this is the phosphorus export that we observed, and we can compare it to this long-term expectation because we have a much longer period of record. And what we see is that only 60% of the nitrogen that we would expect to be transported and 74% of the phosphorus were transported during this main implementation phase of these integrated farming practices. So the importance of that is that if you were just to look at the the nutrients exported during the implementation phase, and you had no historical context to place on it. Now, some of this could be from the implementation of the farming practice, but we think a lot of it comes from just changes in precipitation patterns during this implementation period. But this allows us to get a better handle on what's really happening in the system. And it's important that, hydrology is really important, and if we want to assess if these programs are working, because hydrology is driving how these nutrients are delivered into the streams. So I'm going to conclude. So long term, and by that I mean 1990 to 2013, we know that total nitrogen in northern Missouri streams appears to be flattening. So maybe we've reached a sort of threshold. I'm not suggesting that the streams are in perfect health, but maybe we figured out how to better manage nitrogen on the landscape. Total P is a different story. It's still increasing. And we have these new tools which really help us understand the kind of variability and what's really happening in the system, and that's useful because it really helps you pinpoint where the resources should be directed. And in the short term, and by that I mean just in the 3 or 4 years, we know that nutrient transport follows the planting, growth, and harvest cycles, and those coincide with hydrologic patterns, and that's important. And that most of the nutrients are transported in this mid-February to June time frame, and that if you have a drought, if you start a study, and that's happened here in Kansas City, if you're trying to measure the effect of something and there's a drought that suddenly appears, it's going to affect how you understand things. But if you have a long-term monitoring in place, you can compare that. You have something to compare it to. So I need to acknowledge USGS colleagues, Dan Armstrong, Heather Krimpa, she's in the audience. She's taken over this study from me. Steve Walker with the Missouri Department of Natural Resources, and Steve Hefner with National Resource Conservation Service. And this is an F5 tornado over a veal farm that we took one day when we were out. I've always wanted to see a tornado, and I was very excited to see this, much to the chagrin of Armstrong. I had to convince him that I knew the direction that was headed, and he stuck with me. But it was a fun day because it was going in a different direction than we were. So that's all I have. Thank you.